Hello everyone. Today we will start with a new example. Now again, let me revise what we have done. We have a plate, dimension of plate is 200 by 400 millimeter. You have a circle with a radius 40, and we have two squares by dimension 40 by 40 millimeter. Thickness of that plate is 4 millimeter. New modulus 210 gigapascal. Mass rotation 0.25. Yield stress is 450 megapascal. In my last video, I assume elastic material and I applied displacement at the top here on that plate, and the value of displacement was 2 millimeter at the edge of 400 millimeter in y direction. Now what I have to do now in the second part, or in this lecture or this tutorial, we will again apply 2 millimeter displacement, but we will assume the plate is not elastic material. We'll assume that the plate could go to a plasticity, so we will include plasticity. The behavior will be elastoplastic of plate, as you can see from these tutorials here. So let's go through this tutorial from the beginning. Now I will continue with this tutorial. So we'll go to run Elastoplastic Analysis. Now to run the Elastoplastic Analysis, let's open the model that we created last week. So you go to open, and then I remember I saved it on D, and I think it is here, ABAQUS, and I think this one is back tutorial, yeah, steel sheet, and then OK. That is the model we did last time, and this is a material property here. Remember this, if you remember it, and then that's a mesh. We did a mesh last week. Now, in order to include plasticity in the model, we go to Material Manager. We double click the material we did, which is a steel, and this is the long modulus and Poisson ratio. I will add from mechanical, plasticity, and plastic. ABAQUS will require the yield stress and the plastic strain. So I will assume the yield stress, which is the yield stress, which is, as we said from the tutorial, is 450 megapascal, and the plastic strain at that particular yield stress should be 0. In this situation, ABAQUS will understand that the material is elasto-perfect plastic. What do I mean by perfect elastoplastic? Let's explain that in a graph. Now, that is a strain axis, and this is a stress axis. This is a strain axis, and this is a stress axis. So here is a strain, and here is a stress. Now, How does the steel behave? If you go to a lab and test the steel material, you will have something, the behavior will be something like this. You will get some jump up and a bit down here, and you will have what is called plateau, where the strain increase by constant value of stresses, and then you will have hardening. So I think hardening, okay. Now at this particular value where the stress is constant with increase of strain within that domain here from here to here, this is yield stress. Well, this is Fy, which is well known. Now in ABAQUS we will not model the whole that behavior including the hardening. Usually we will model from here and constant. So we ignore that hardening. So what you have to put in ABAQUS, you will have to put the yield stress as this value 450, and when you said is zero plastic strain, mean that elasto-perfect plastic. That is the behavior you apply in ABAQUS. Say okay and dismiss. Now you need to go to step. Since you are doing plastic behavior, elastic plastic, therefore plasticity will be generated in that plate. And so if you click on the step manager and you double click here and you go to incrementation, you have increment size and maximum increment size initiate maximum. If you leave increment initiate as 1, which means that the 2 millimeter will directly 2 millimeter applied load will fully applied on that model, and this lead to on convergence problems since there is a plasticity. I explain that in details here if you go to my tutorial. So what I say that you are conducting plastic analysis, a non-incremental iteration procedure is needed. So because you are doing plastic analysis, so a nonlinear incremental iteration procedure is needed. So I will not allow for the whole load to be applied, so the initial value of the load, which is 0.05 times 2 millimeter, which is 0.1, will be initially applied and then incrementally increase over time. Now how much incrementally increase will be automatically produced by the software ABAQUS. Now I will say that 5% of the load, which is 0.05, 5% of the load is the maximum increment, and 0.0001% of the load will be the minimum increment, and 5% of the load applied is the initial value. So when ABAQUS do an automatic incrementation, he will multiply the initial value, which is 0.05, by the applied load, which is 2 millimeter, and then provide an automatic incrementation, and that the value of that incrementation varies between the minimum and maximum. Okay, so when you have plastic analysis, you need to provide a nonlinear analysis, and you have to identify the incrementation. In the elastic analysis, you don't need to identify the incrementation. Now, if you go to mesh, click here and make sure that you are using quadratic and reduced integration. Now, if you go to job, let's back to the load and click on this, actually the boundary condition manager. If you double click on the prescribed displacement, you will have to see the 2 millimeter applied displacement from the last week. Dismiss and close. Now go to job and then click on the job manager. You create, for last week we did case 1 elastic, and now we will do create case 1 again plastic, case 1 plastic. That's the name of the job, and continue, accept, and submit. I would like to save the model. It seems still submitting. Now it is running. Let's see monitor, and let's monitor what's happening there. The good indication that it is a completed input correctly. Yes, that's running. So this number of increment, number of iteration to solve the problem, total iteration, total time, and dot proportional factor incrementation. What do you notice? That the incrementation doesn't go beyond 0.05. That's what we set it up. Now everything is finished. Let's dismiss and let's get some results. Interesting. Got this result. If you click in the contour plot, you will get the stresses. Now if you go to here and you click on PE, which is plastic PE, and you will have actually the plasticity over this circle and some plasticity over the square. So what I want to do, I want you guys to go into your last page of the tutorial and I want you to fill up the elastoplastic without refined mesh. You need to find out you need to actually at this point 1 2 3 4 5 6 7 you need to fill up this table, which is plastic stresses. S22 stress in two directions, y direction, S11 stress in the first direction, U2 is a strain displacement in y direction, and PEEQ, which is equivalent plastic strains. Now so the PEEQ, this one, equivalent plastic strain. So that's PEEQ. What do you notice? That it seems to me around the circle most plasticity. However, it must be there's more plasticity also a lot around that square. So what shall I have to do? It seems around the square we need to refine the mesh. So the question is how to refine the mesh. But before we refine the mesh, let's pick up some data and remind ourselves how to pick up data from here. So if you go to stresses, which is von Mises S, and then let's click actually on this undeformed shape for a moment. Now I need to pick up the stresses at this point and this point and this point and this point here, what else, and some points around. Now von Mises stress, if I want to look for Mises stress, then you go to query information, you go to node, prop value. Choose nodes. Now if you zoom in, you can see 297 von Mises stress at this point, 372.666 at this point, 355.4 the von Mises stress here, and 537. So you can find out the stress at any point. If I want the stress in XX direction, so you can go from stress and S11. Again, it's deformed, so I will make undeformed shape. So you go here, you find is 93.84 von Mises stress here, and the stress here is 108. Stress here is 64 minus, and here is 3994 as tension. If I want the stress in y direction, so S22 undeformed shape, you click here, S223 tension, 268 tension, 293 tension, 359.8 tension. So I could find out here the stresses. And now if you want displacement, you go to here and you and choose not magnitude, choose U in the Y direction. For example, click on deformed, zoom in, you can find out the displacement 1.2 millimeter, 0.9 millimeter, 1.91 millimeter, 1.02 millimeter, and finally 1.76 millimeter. If you want equivalent plastic strains, you click here. Also, you can find out equivalent plastic strain is here 0, which is weird. Of course, this is small value, and this is 0.001, 0.0034. It seems to me the highest is here 0.13, and if you go down here, it's very small value also of plastic strains, and here's 0. It seems to me is that we need to refine the mesh. Now we know here now how to find out any point what is the stresses now and strains and displacement. Now let's refine the mesh for the same example. So let's go to mesh, close this query, go into seed edges. You're gonna ask you which one you want to see the edge for. You click on this edge of the rectangle, square. While you clicking, you need to click the shift for multiple element selection. Click here, 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 and say done. Now choose by number and double. Number of elements is 40, and choose the PS ratio is 8. So in this situation, it seems there's an issue. We need to select this also. It's not selected, it seems, so let's cancel it. And again, don't forget to press shift and done. Double by number 40, the PS is 8, which means that the more mesh will be toward the edge, and you need to make sure that the arrows here goes toward the corners, and then you said okay. We'll ask you, do you want to delete the previous mesh? Yes. Do you notice that we will have more mesh in the corner, more seeds in the corner and less in the middle? Now let's increase the mesh around the circle also. Click on the circle and say done. Just say none, and then say 40 element. Said okay. Say done. Now you go to here, mesh part, and you say okay. Let it mesh automatically. Brilliant. You notice that the edge was meshed more. Now let's go into job. Before that we save. Now we did the elastic case beautiful last week. Now we did today the plastic analysis. Now we will do again the case 1 plastic and refine mesh. Refine mesh, continue, and okay, let's call it plastic refine mesh. Let's submit it and wait for the results. Let's monitor. You notice that the time increment is no more than 0.05 and no less than 0. Or 10 power minus 5. It seems there is a convergence problem, so we'll carry on. When you see 1 you mean that it's the first iteration starts but doesn't converge on the first iteration, so it does the second iteration, so it's still in the first increment, the 15 increment number 15. Now still running takes more time because there's more number of element. So almost half of the load now. Now we are increment 25. The increment 26, the first time tried, you notice that the maximum is 0.05 increment, the maximum increment. Now almost finish. Getting closer. You see that the maximum increment is 0.05 as we set it up. Now when you say 1 mean that you finish the whole process loading and it's completed. So you can now say dismiss and just get the result for. You click here. You will see it seems to me there's more stress distribution over here. If you click on PEEQ, now it's not clear to me, and then we can click on the contour option and get a limit and specify as 0.01, which is 1% of plastic strain, and then it's a plastic strain about 1%, and then okay, you will clearly see the plastic strains around here, around the edge here, around here. Now if we need to find out the stresses around the edges or the stresses of these points, now let's click on S and then on Mises and click here undeformed shape. You click on query, node, pro value, choose node, and then zoom in. Now you can find out the stresses at this corner was 4.33. So you could make a comparison with the previous result. Zoom in, zoom out. 346 as a circle here, 455, etc. If you want S11 also, you can find it out, and you click on deform shape. You can find the stresses, for example this circle 22, and then S22, and the deformation, etc. And the equivalent plastic strains, if you go to here, let's zoom it a bit in, 0, now a small value. It was small before, around these points here it was small, now it's bigger. That's because of fine mesh. Now we close it. If we need to find out the load displacement relationship, so as your load applied, what and as the displacement applied, what is the load or reaction forces, in order to find out the ultimate load capacity of this plate. So please follow me in these steps. Close here, add your result, go to tools. So firstly, let's find out the forces, the reaction forces. So go to tool, XY data, manager, go create, ODB file output, continue. Choose now unique nodules. Now you need the reaction forces, so you get the reaction forces and you choose the reaction forces, and of course in Y direction. Now you need to choose the element. You go into element node and click on edit selection. It's very important. Now go to your model and you need only the node at the top surface where the load is applied. So you click down here, window, only the top nodes, and you click release. We need mistake that we don't need these nodes, so click upside again, we click over here, so we selected all the points up here, and then you say done. You have 41 nodes selected, and you said save and said OK. Now these are the forces or the reaction forces at each of these points, but I need to sum up all these to find out the total load. So you go to create, operate on XY data, continue, you click here in the window, you go down here, and you will find sum. Click on the sum, and you click here, and you keep your mouse clicked, right click or left click, you keep a click, and you get down here until the end, all. Okay, so you highlight everything. Now you see the here, and you apply add to expression. Now when you add to expression, you will have these into Newton, the summation. So you go to the end here, you click at the end, and then you divide it by 1000 to have the load in kilonewton. So save as, call it as a force, and then OK. Now close this one, you don't need it now. Now you have the force. If you double click on the force, it will give you the forces over time. And what you notice that the maximum force is 212 kilonewton. So this plate can sustain up to 212 kilonewton. So let's cancel this. Now what I need you guys to do is you need to take all this data except for the force and delete it. Keep the force. Now I want the displacement on the top here, so you go again to the XY data from ODB file and you unclick this one, and then you need to click on U, and then you click on U2. You click on element nodes, you edit selection, you click outside and edit selection, and then select, for example, this node in order to find the displacement at this particular node. Then OK, and save, and say OK. So you will end up with, if you double click, you will have the displacement, applied displacement. Now let's copy this applied displacement. It's a clip copy. Go to Excel sheet, right click. So this is your displacement. Now close it and you go to the force, double click on the force, and you take your whole forces, copy it, you go here and you paste it. Now this is the displacement and this is a force. Now let's draw the relation between them. So you highlight all of these, you go to insert, scattered, and for example choose this graph. Excellent. So what do you see? That as the displacement increase, the load increase, and once it become at this particular point, as the displacement increase, the load doesn't increase, and the maximum load capacity is 212 kilonewton for this. Okay. Now, so let's close it and let's delete these. Now, here we finish the case 1 when we apply load displacement control. Thank you.